Okay, my friends, this is going to be fun. This is Don Lincoln. He's with Fermilab. That's a national government agency tasked with trying to find particles and so forth. And he does a lot of videos, and I've interacted with Don long ago. And this is how do magnets work? How do magnets work? And he explains all these things with the current theory that they have, and I do not go along with that theory, and I will show you precisely why. Now, this goes back to long ago. This was about 1970. I came up with the conclusion about dipoles, and that's all this is. Everything is a dipole, and I called it Dipole Electron Flood Theory, where there was nothing but dipoles. And this go, like I say, this is some old stuff, and I did a lot of this, a lot. I did everything into chemistry, into thermodynamics, into quantum, the whole 9 yards. Now, there's two types of intermolecular forces. It's dipole interactions. That's all there is. And then you have polar and nonpolar bonding, which is the source of magnetism. And the transfer of energy is from light to atomic vapor. Light itself has both of these sides, and Don Lincoln himself proved this. I'm going to show you his article. Now, this is my paper I put back up on academia.edu from 2019 about dipole electron flood theory. I think I called it nucleatron theory, or like nuclear electrons, because they are. The nucleus has electrons just as well as the orbits. So he wants to ask about how do magnets work. Let me show you how they work, first of all, because I can actually demonstrate how they work, showing them in action, and then we'll talk about what he has to say about it. Okay, so this is Fermilab, and this is their vision, and their mission is to lead the world in neutrino science with particle accelerators. They lead the nation to development of particle colliders, and they're used for scientific discovery. We want discovery. Advanced particle physics through measurements of the cosmos. Now, this is Fermilab. This is the article that Don Lincoln did, who is the guy that's, here it is, right, from Don Lincoln to Fermilab. Physics in a nutshell. He does a ton of these things. Now, here's his point particles. You see these particles right here? These are the ones that we found. Now, these are supposed to be the smallest particles that exist. And he's talking about the field of particles full of what confusing names of all kinds of things, which is true. It is very confusing. These are the only two particles that exist. Those are the only two particles that exist right there. And he's right about them. This one here is a fixed particle, never changes size. It's almost all the mass. This has virtually no mass whatsoever and has all the energy. It can get big and it can get small. It can get energetic and it can get just quiet. This one is just a bowling ball. And that's exactly what he says. And again, this is Don Lincoln. He says, if you have a question. Now, in summary, extended particles, the black one, has a fixed size. And I'll show you, we did this research and found he's exactly correct. They may have a fuzzy edge around them. They do. That's the color. The point-like particles are mathematical extractions with zero size, and I have to pretty much agree with that. But even zero-size particles have an extended field, and the field is what gives you the energy. It's due to the effect of the field surrounding them. So they have the energy. They are the ones that have all the energy. The black particle is nothing but mass. The white particle is the energetic part. That's the one that does the burning and does the electricity and static and all that. And it can separate from the black one. So normally these two are together. It's called a dirac. Let me show you what this is, and then I will show you what a magnet does. A magnet is nothing more than this right here. It's got a red side, and it's got a black side. Right? And on a bar magnet, it's one side and then on the other. I really can't explain how these particular bar magnets work, but I can tell you what. When you put them side by side like this, they push apart. Right? Even if you have them this way, they push apart. Can you see that? Yes. All right, but once you go that way, they slam back together. And whether or not they're that way or this way, they slam back together. So there's a white and a black, and they just want to be attached together. That's their whole mission in life. And that's, I call that the strong nuclear force, because this is inside of a nucleus. This is not just something that's floating around outside little electrons. This is a photon right here. Let me show you what we discovered. And two of these together, this one and like that, two dipoles together make up a photon. Okay, let's just start right here. What is particle physics all about? And what are these super colliders all about? Particle physicists use gigantic accelerators like CERN and Fermilab and Lawrence Livermore and so forth to investigate and try to find the tiniest particles that exist. What they're looking for is the tiniest particles that exist. Can they actually see them? It says the search for the basic building blocks of matter. What builds matter? Goes all the way back to the philosophers of classical Greece. Today physicists use enormous particle accelerators to study the tiniest building blocks. So we want to see the tiniest pieces that exist. Why start with protons? Why not start with light? All right, so we're looking for the tiniest particles, the smallest particles that exist. And light is actually energy, which is made of the small particles called photons. Let's look at a photon. Okay, if you come up looking around for a photon, you're going to see all these kind of things. What exactly is a photon? What is a photon in physics? Photon emissions, wavelengths. What is a photon? Definition, facts, da da da. Well, I don't see anything that looks like a photon to me, but I will show you actual photons that were seen during experiments. Okay, we're getting a little deep here, but this, you have to understand what these particles are made of. They do not understand what even the particles are made of, so how can they understand magnetism or anything that they're talking about? Okay, so don't forget, light is the smallest particle that exists, and again, this was Don Lincoln, and they saw these two particles. They know they're there, and he showed them in this article I just showed you. And here they are as we did these light experiments. And we were able to see these using what's called CMOS, complementary metal oxide silicate substrate, to receive these photon energetic values and not destroy it, because we're only using light. They could not use CMOS originally at CERN. And that was, I went to University of Geneva, and I interacted with them, and I told them what we were doing. I showed them all our stuff, and they said, well, how could you see this? And I said, well, we use CMOS. And they said, well, you can't do that because it'll destroy the CMOS, these high energies. And I said, no, we use light. You guys used protons, and when they break theirs apart, instead of hitting this with one or two of these little particles, they hit them with a chunk like that. And of course it destroys the CMOS. But they did upgrade. They actually did an upgrade. And they also put in the superconducting magnets to focus. This was a focusing upgrade. They did both upgrades at the same time. It took 3 years. And the other upgrade was to use the CMOS detector developments. What they had to do was harden the CMOS so they wouldn't be destroyed. They're still hitting it with big chunks of particles, but they have some kind of filter on it to harden, a major upgrade to increase instantaneous luminosity. And that's what we have. We have luminosity coming out of our earlobes. If you can't see luminosity right there, my friend, I don't know what luminosity is to you. We started with this, you couldn't even hardly see it, and we ended up with this, which is Don Lincoln's black particle separated from the white particle. They're called muons and electron neutrinos. Together they're called a dirac. I'll show you. When we put them through our Venturi, because the fixed particle can't change size, if this is tuned correctly, only the white can get through, because the white can squish down and get big and do all that, and it's squirted right through there, and the black just keep bang, 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 squirting it out. And here is where the major attraction, this is gravity, well, you call it whatever you want, but it is magnetism. The black is coming back to the white. That is what magnetism truly is. This is the most magnetic you can possibly get. And this magnetism is nothing more than electricity. When you take electricity, you have a positive and a negative, and it pushes the negatives through, or the negatives get sucked to the positives, to ground. Basically, negatives get sucked to ground, and the black is the ground. You have to think of it however you want to think about it. Now, AC works a little different. Alternating current goes pushed back and forth. DC goes all one direction, and it is nothing more than this right here. It's virtually nothing more than the white particles moving along to find the black particles. All right, and this is nothing more than light. So we're at the bottom end of the spectrum as far as energy goes, as far as particles goes. And I'm telling you right now, a black and a white one, just like that, one in each, is what we were always considered an electron. We never knew the black part was attached to the electron. We always thought the electron was just the glowy, burny part that caused electricity and fires and all that stuff. No, the black is along with it. Now, we were able to separate it. All right, so you see it there together. There's no question they're attached together. And that is light. There's no question of that. That is from a red pulsed laser. And the reason this one's getting glowy is because of that in front of it, this stuff it's hitting in front, all the fields that it has to crush its way through. And that's why light glows. And when it bangs against the wall, it gets real glowy, and it bounces back as a complete particle. Because once they're attached together like this, they're like two-bar magnets. So we're back to magnetism now. And when those two-bar magnets are stuck like that, there's just one surrounding field that surrounds the whole thing, like a balloon. When it hits something, it bounces back. It depends on how hard the thing is hitting that it is, and what color light it was in the first place, how fast it was spinning. Because light spins. Light doesn't flap like a wave. Light spins like this. And I can prove all these things I'm saying. Because we got pictures of all of them, because we use the CMOS. And they upgraded to use the CMOS too. They're using this, and they got all their spectacular results now. Well, not as spectacular as ours, because we started with light. We started with light. All right? All of this stuff we did here, all of these different colored pictures are light. So, now, this is a Dirac neutrino, and this is a black and white particle. Now, then they have another neutrino phases. They call them majornas. They're in between. They're all kind of neutrinos. But this is a true Dirac neutrino, which is an electron. All right, and here they are right here. All right, that's a Dirac, and that's a Dirac. They're both magnets. Back to back, they make up the photon. The photon is light. These are as close to the smallest particles as you can get. If you could separate these, you would have the smallest particles that exist. And guess what? We separated them right there. The black came away from the white. It comes back together here. That is fission, and that's fusion. There's no other way to look at this. And, you know, I've been excluded from being able to talk to Fermilab and all the rest of them. They don't like the fact that I did this for virtually nothing, and that I can prove what I'm saying. Because here's the photons. You see the black and white? Let me turn this light off and get it a little bit better look to it, I believe. Now, you see these here? These are neutrinos. That's a true photon. And the reason the photon is getting to be the good photon phase ahead of the Venturi, ahead of the wall, basically, where it would bang, is because it's being accelerated. And this is the Venturi. Now, these up here are not being accelerated to this extent. These are down here right directly in the path of acceleration. So they're getting hot quick. These are just sort of coming along with them, but not in a direct focus like the bullet coming straight through. That's why we can see these. You wouldn't normally see these photons until you had the collision. But because we're exciting them past the speed of light, basically, they are showing up as photons prior to actually bouncing. That's my take on it right now. But these are neutrinos. They're not quite photons. That's a neutrino. That's a neutrino, neutrino, neutrino. All of those are. And these are the same exact identical particles as the green. All right, here's the green coming in. And these are the neutrinos of the green. They're not quite focused yet. I mean, they're not quite puffed up enough. This one here is exactly, you saw the red, there's no difference whatsoever, none, zero. This one's getting ready to flip. You see the bottom part is getting charged up. It's going to flip. As they go through the air, the leading white part gets charged, then it flips, and then the diminished white part comes in front and gets charged up. And they just keep, that's what makes them spin around as they move. So the particles are the same, no difference whatsoever. Only these are very powerful compared to the red. show you this, but just so you understand, the red just is no power whatsoever. It's just not spinning fast enough. And here's the way they look when they are spinning. All right, they spin like this. They spin like this, coming this way. And the red ones are way out long like this, and they're just, when they bang into you, they're not really slamming you. The blue is like a sizzler, zzz, right through it, and the red is kind of fast too. I mean, the green is kind of fast too, and the red is slow. And they say red shifting means that the planets are being pulled away, stretching the light. I say no. The light is coming at us, and it's just getting slower and slower and slower and slower and slower and slower and slower as it comes towards us. But Einstein literally broke physics by saying light can't slow down, can't speed up. I can show you, there's no question whatsoever it can speed up and slow down. It's 100% certainty. 100% certainty. All right, here's light slowing down. Here it's coming in really fast and hot. And they all do that. They all and they can speed up. You see it speed up. No question it can speed up. Here it is right here. It's coming in slow, and it's zip, pulling itself right out of its own wave. And here, extreme luminosity, which means extreme energy. And here, the black separated from the white is fission, and here's fusion. This is raw electron showers. They claim if you can get electron showers, you can get up to trillions of electron volts. This should be free energy. I don't see why we can't get free energy by using just a very simple device, something along the lines of this. The laser shoots out the particles. The Venturi restricts everything but the white. The black just keeps bang, 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 and we can regulate the speed of the pulses to how it's best to force these particles to slap those white through, because only the white can get through. Now, on the other side, we need to force that white down into a battery. And it's the exact same situation as you do in your car or anything that absorbs electricity and makes it powerful and makes it energetic. Your car weighs, let's say, 4,000 pounds, and you've got a 500-mile charge on it. All right, and it weighs 4,000 pounds. You drive that 500 miles, you come back, it still weighs 400 pounds, or whatever it weighed, 5,000 pounds. You charge it back up again, it still weighs, it never changes. All we're putting in is the white. The white has no mass. Exactly what they said at Fermilab. He says this is a point particle. It has no mass. That has all the mass. The fixed one. I don't disagree. I just find it, we should be able to do something more than just talk about this and look for these big particles. It's fine to smash these particles apart, but what they're looking for is these particles. They're looking for these particles. Why start with these? You just get nothing but actually trash. Let me show you something. You see this? This is what they're using, protons and neutrons. And they're coming around and around and around and around, and bam, they hit like this. When they slam like this, they get all of these particles, and they only get a very small percentage of them actually hitting. They actually put in focusing magnets at the same time they upgraded for the CMOS. And again, I told them about it. I said, we focus and we use CMOS. And then 3 years later, they had focusing and CMOS. And it's a bang like this, and they're seeing huge particles like that. You see this? We are seeing the single particles, because we started with these particles here. We didn't start with this. So here they're seeing a big chunk come off this way. And this is what destroys the CMOS. That's why they couldn't use it originally. Now, the next thing that happens is all of these little bits and pieces, which maybe you have 3 or 4 of them come together out here. And that makes this. And 2 of them over here make this, and 4 of them over here make one of these, and a half of one of these. And I mean, it's just a particle zoo. They call it a particle zoo, and they name them all kinds of crazy names. The only 2 particles that exist is the black one and the white one. That's the only 2, and they make everything. All right, so it's just like they have found them. They know they're there. They just get them in a big pile of debris, and they don't know where they came from because they're not starting with light. We see them start as photons. They're guessing at photons, I think, but I don't know if they can actually see them. We can. And here they are right here. All right, now, again, those are the red ones, and we see the green ones, we see the blue ones. And we see them actually separate right here. The black and the white separate from each other. Only the white can get through. And right there, that's raw energy. And that's all you want to put in your batteries. I can't see why we can't use this. I really am perplexed at the resistance to look at this. Now, here's what they see at CERN and Fermilab and all the rest of them. They're smashing, again, these huge particles. Boom! And they see all of this debris come out. And it's hard to make any sense of it because they're seeing some of them take off, never come back. They're really blue and the greens and so forth. They're powerful enough where they just go. The reds are sort of just hanging around anyway, so they just sort of bump away and then they all recombine back into the mix. Well, that's because they're starting with this. Why not start with this? And then you're going to see the actual particles, which I show you. And again, this is not a pipe dream. This has been done. And here they are. And not only that, once we go through this Venturi and the white comes out, you want to see white? I'll show you some white on steroids. Here it is right here. I call this Higgs on steroids. These are Higgs fields. They're talking about coming up with maybe 25 million Higgs fields after all their upgrades. In a year, 25 million. We could do that in 10 seconds at least. Look at this is instantaneous. These are all Higgs fields. And here's the ones from Fermilab, the same thing. They show these Higgs fields. They're all these little circular patterns. But they're just big globs of things for them. For us, we're seeing the Higgs fields of the actual particles reuniting. The white is reuniting with the black. And that's what creates the Higgs. They have it the other way around. They say the Higgs fall apart and decay into a black and white. No, it's the other way around. The black and white come together and they make the Higgs. There's not much that's right in particle physics right at the moment. And then they talk about light coming through space, through all these fields in space. And now they're talking about quantum waves, or I forget what they call it now, gravity waves. Which is, yes, that's right. They're all out there. They said, you know, but I've been posting this for years. Years. And here's what we do. I'm not making up little cartoons like this. But see the black? You see the white over here? Everything's black and white. And I think they're starting to understand it. Now look at this. This is our actual. This is the reality of space. These are fields. These are magnetic fields. And they get weaker and weaker and weaker as you get further and further away from the source. We know that. A magnet will only work to a certain distance and stops working. And this is basically what you got here. And it's very intense, very close. And it comes out to almost nothing. But you see, everything is a dipole. Even these, you see these over here? They're little dipoles too. And they all have fields. Every one of them has fields around it. And this is a strange one. I got a hard time with that one. And this is the moon, and the moon does not spin, so it doesn't have magnetic field around it. They have to spin to create the magnetic field. However, it is moving in this direction, and I know that for a fact because the blue is being compressed. The light is being compressed, shifting to blue. Normally they say everything's going away, make it shift to red. Well, you could shift to blue too. But everything is not going away from everything else. The red shift is coming as light just naturally slows down, coming through these fields. That's what the red shift is. There's no way in the world we have any idea where we are right now. These long distance telescope or Webb telescope and all this stuff. Well, now we know we can see 4.8 billion years ago. No, they don't. They have no idea where we're looking. These stop and slow particles down all over the place, and they're everywhere. The galaxy is saturated with this stuff. It's everywhere. It's everywhere. We're in here somewhere, and all the light coming to us has to get through all this stuff somehow. We think we can just look through it and then nothing happens to that light. That's literally insanity. If you think light can come through all that soup and not be affected, I could show you light being affected right here, just in the natural gases. It's slowing down. The blue is slowing down. The red is sped up and the green sped up going through the Venturi. So Einstein is the problem here, and Fermilab is not helping either at the moment. All right, so don't forget, Don wants to know, what is magnetism? How does it work? It is these two particles. And I never really thought you could separate the two, but you can. And I always was able to magnetize my screwdrivers. You take a screwdriver like this, you buy it at the hardware store, and there's no magnetism. All you have to do is take a bar magnet and stroke it this way. You stroke it along like that. And then you end up with a bar magnet. All right, and eventually they lose their magnetism, and especially if you're banging them a lot, they bang, and the electrons can shift around here. And they actually sell demagnetizers that you can put around here so that they won't be magnetic. Once you magnetize them, you can demagnetize them, and all that is pushing the particles. So what did we do when we stroked this? All right, we're pushing either the electrons forward or the black particles forward, one or the other. It's a separation of the charges. All right, and the tip, like in other words, if I push this way, and that's the positive, the black is up here and the red is down the bottom. If I turn it around, it would do the same thing. I'd still have the same kind of energy. I'm pushing the same particles up. So the electrons must be being forced to the end. That's all I can think of. Well, you know what? Look at that. That's interesting. It lost some of its power. Wow. Hold on a second. I gotta investigate this. Well, you investigate it with me. All right. Before, I could put this on there and it would just hold it right up very, very well. All right. It's not that powerful now. Let's see. So let's take that side and drag all the particles down. 1, 2. We're dragging all, let's say, the electrons down. I don't know what we're doing, but let's see how powerful it does get. All right, so now let's see what we got now. All right, it's actually, well, maybe it's a little better. Let's try the black going the other way. Let's try just once and see what happens. I could feel a difference. See it fall right off? See it? Watch. This is how I learn stuff. Look at this. Watch it. Now it's just falling off. It won't even stay. That is so interesting. Look. I can't even get it to stay. And all I did was, watch, now I'm going to magnetize it and it will stay. Watch, I can't, it's totally demagnetized. This is freaking me out. I worked with this stuff my whole life, and all I ever did was magnetize. I didn't care. As long as it was magnetic, I was good to go. Now watch this. All I did was take this and put it backwards. No, I guess I got it in the right direction this time. Let me go this way. Oh yeah, see, now it's totally demagnetized. Now let's see the black side going up this way. That magnetized it. Alright, so now I'm going to flip it over. Now, see that? It just totally demagnetized it instantaneously. See it? And now it'll be completely demagnetized. Well, very interesting. I can demagnetize it and magnetize it. So the electrons have to be, oh boy, I tell you, this is I'm gonna have to go back and look through this, because this is a revelation. Watch. See that? Boom, gone. This I must investigate. Now let me show you something about meteorites. This is a little tiny iron meteorite. Now it's not magnetic, it's iron, so magnets are attracted to it. It doesn't attract other iron. It's just made out of iron. And iron has some extra electrons, it appears, or a lack of electrons. I got to dig into this a little deeper, because iron you can send electricity through iron. It's a pretty good conductor. And secondly, it can become magnetic, which means you can move electrons back and forth through its structure in iron. Because this is nothing more than steel, iron, same thing. And we can do the same thing with this. We can make this extremely magnetic just by dragging across this stuff here. And then you get it becomes extremely magnetic. All right, this is maybe, let's try this way. You see? All right, so, we used to have to use this because I worked on a lot of very sophisticated, tiny little equipment where you had to go way down deep inside with screws, and they had to have them magnetically attached to the screwdriver. You lose them. So, you know, I've worked with this stuff all my life. It's not like something I don't understand. It's just that I'm starting to understand it a little better now. So this is nothing but two dipoles, and every dipole is a bar magnet. Let's see what Don has to say about bar magnets. Okay, so I showed you the article by Don Lincoln, and here he is talking about electromagnetism and permanent magnets. Now here he goes. I'll let him make his statements, but this is Fermilab, and again, this is Fair Use Act. I'm just using it for educational purposes because I think this needs to be investigated. Listen to what he has to say.
In a recent video, I described how electromagnets work with a focus on the length contraction predicted by special relativity. That topic is one of my very favorites because it demonstrates relativistic length contraction with velocities under a centimeter per second. But many of you asked for an explanation not of electromagnets but permanent ones, and that's a very interesting question. Let's dig into it.
I agree, Don. And I want to make another statement that special relativity and all that stuff was by Einstein, and he's the one that broke physics. You can accelerate and slow down light. I just showed you. So let's see what Don has to say. Okay, how do magnets work? Now don't forget, Don is mainstream. He totally rejects my claims about light for some reason. I show exactly what he did, but he rejects me. Here goes.
The question of how permanent magnets work is certainly interesting. Magnets most definitely seem like magic. It turns out that a lot of things have to line up just so to make a permanent magnet. The relevant phenomena involves fundamental particle physics, atomic physics, and small-scale physics, sizes in the ballpark of a fraction of a millimeter. It's all very complicated, but hopefully I can make it clear. So first, the basics. Magnets have two poles, a north and a south.
All right, I don't disagree with that. And magnetism primarily is, I never thought you could split these two apart. I never thought they could. I thought they were just together. Because every time you break a bar magnet apart, you get two more bar magnets. You break those and you get another batch of bar magnets. They always become a positive and a negative, no matter how many times you break a bar magnet. But when you get down to where we are with the light, there's no place left to go. And these can separate. And then the black one goes and the white one goes. That's the only time, and that freaked me out when I saw it because I never ever expected them to be able to split. So he's saying, so first, the basics. Magnets have two poles, a north and a south. I agree with that.
You can't have one without the other. Like poles repel and opposite poles attract.
Now, you know, when he says you can't have one without the other, when you get down to the subatomic realm where we did with the light research, you can have all north and all south separated, just like the electron showers and the black particles. So that's not exactly correct. Here we go. So he says you can't have one without the other. Like poles repel each other and opposite poles attract. I agree with that.
And two magnets pointing in the opposite direction cancel each other out, leaving no magnet at all.
I don't totally agree with that. The two of them together, actually, when you're down in the subatomic realm, make a photon. And a photon it's not really magnetic. It bounces. It's got a field around. When you slam these two together in the subatomic realm as light, photons, it will have a huge field around it. When it bounces into something, it bounces back. That's why we see it. And the bouncer is the electron part. The white part makes it bounce. The black part is just a carrier. All right, so let's see what he has to say now. So he's saying it would leave no magnetic at all. And I have to agree with that.
Magnets are made of atoms, and therefore the origin...
Wait a minute, I got to tell you something. This just brought back something to me. You see what he's showing you, a bar magnet? When I was up in Alaska working on Yankee Hercules missiles, we had these huge, and I mean gigantic, you could just barely lift them up, bar magnets. And they were big, heavy-duty things at the end, and then they came down to like a smaller tube at the bottom, and they were rounded. So, and they were absolutely gigantic. And boy, we used to play around with them and push each other away with the fields. And you'd be this far away, and you could push the other guy away. You couldn't get any closer. The absolutely unbelievable field. So here's what happens. Me and my buddy Brick, we grabbed one each, and we ran across the room at each other as fast as we could run. I mean, unbelievable. And we hit just like that. And of course, the magnets didn't actually hit, but we just went flying, and it was, we were laughing like hell. And we get up, and they lost 90% of their magnetism. We forced the magnets to, and these are expensive. So I'm confessing to it now. I think there's some kind of, law that they can't get me after so many years. But that was kind of fun. And so you can knock the magnetism right out of them by pushing the particles that have collected here. They're collected up here, and you push them, and they start to filter back into here, and you've lost most of your magnetism. All right, so magnets are made of atoms, and therefore, okay, so the magnets are made out of atoms, and therefore,
are made of atoms, and therefore the origins of magnetism must come from the atoms, or the constituents of atoms, and how they move. The relevant bits of atoms are electrons and protons.
This is where he's wrong. The protons are not like big positive things, and the neutrons are big neutral particles. No. They are all made out of these dipole electrons. So out here, that's fine. You can have other electrons out here that want to get in. And there's just so many positives and negatives in here already that they're stable, and they don't want them to get in. And that creates a cloud. They say, I want to get in. They say, no, you can't get in. I say, oh, we really want to get in there. They say, no, you can't get in here. You can stay out here. The black particles seem to attract more than the white. The black is really sucks in the white. So any white ones on here, they're going to want to get in to a certain degree, and then they coat the surface of the actual particle that's stable inside. That's what a stable atom is. And when I say stable, every one of these has isotopes, and thousands of them in some cases. And what is an isotope? An isotope means that it's not exactly the same particle, like ferrous oxide, iron is not just exactly a certain number of protons. It can have all different weights and still be considered iron. And that's because iron in its normal fullness is exactly this number, whatever that number is. But you could take 2 or 3 or 4 or 5 or 10 or 20 or 30 or 50 or 1,000 of them off of here, and it's still going to be considered iron because it still has that same weight range, but it's all isotopes. Isotopes in there that, they're stronger or lesser strong magnetically. And just think of isotopes. There's a zillion of them. And that's what actually accounts for the way life can work. Because when you break down particles in your body, you're breaking them down with enzymes. And they're breaking down little bits and pieces off of actual atoms. Enzymes are fabulous things. But anyway, let's get back to this. Everything is based on these two black and white particles. That's the only thing there is. That's all there is. So he's saying that they have an electric charge on both of them. Here we go.
Both of which have electric charge, and both of which can move. Moving charges generate magnetic fields. I made a video about that. It was
I agree with that.
A cool video, by the way. So let's see if the moving charges of the atom play a role. Let
me just show you the magnetic field that a moving particle does create, because I can show you that right here. And here it is. This is a single wave. All right. Pulse red lasers. Now, there may be 1,000 particles in here, which are the dipole electrons. I don't know how many's in here, but every pulse of light comes out and creates this field around it. And the field is because it has to plow through all these other fields. And that's what that's all about. So this is strictly light forcing its way through the particles that are in front of it. And out in outer space, just like Don Lincoln says, it's a quantum foam. It's empty space is not empty. It's saturated with these particles. Not in these quantities, but there's still enough of them out there that every particle that's coming through it, it has to push them out of the way. It's going to slow the particles down. Okay, Don is talking about protons, which he thinks are like one big ball, but they're not. And he's correct. They're thousands of times bigger than what we would consider an electron. But because all of that together, these are electron dipoles together inside of here. So a proton consists of 1,823. So he says it's 2,000. He's up in the right range. Here goes.
So the atom play a role. Protons are about 2,000 times heavier than electrons, which means...
All right, so he's saying they're 2,000 times. I say 1,823. But every one of the electrons makes up part of the proton. So at 1,823 of them, it makes up what they consider to be a stable proton. And for some reason, it's at that number of particles, and they lock in. And they become pretty stable at that number. And then everything is built on that number up through the periodic chart. But hydrogen, is only that's 1,825 or so particles. It's not just one proton and one electron. It's 1,825 dipole electrons. And then you get up to helium, it's 7,350, somewhere around there. By the time you get up in here, you're into hundreds of thousands of particles. Because every proton is made of 1,823, every neutron is made of 1,824. All right, so here's he's saying they're about 2,000 times heavier than electrons. I can go with that, which means they're harder to move. All right, so let me go back here a second. Here he goes.
2,000 times heavier than electrons, which means that they're harder to move. So the motion of protons is basically irrelevant. Well, what about electrons? Their motion is much greater, and if an electron orbited an atom like a planet orbits a star, that circular motion would make a magnet. But electrons don't move that way. Instead, they're found inside clouds.
No, that's not correct. They do move exactly that way. You want to see how an electron moves? Here's exactly how it moves. All right, so let's go back to here. The motion of the electron is much greater.
About electrons. Their motion is much greater, and if an electron orbited an atom like a planet orbits a star, that circular motion would make a magnet.
All right, first of all, he doesn't understand the particles. The electron is not separate from the muon neutrino. There's electron neutrino, muon neutrino, they're attached together. It's not like one of them can just orbit another one. They will never be separated unless you do what we did or do what they did, smash them to bits. But we smashed ours from just the two black and white particles, which we could see of them attached together. So this is not a representation of reality whatsoever. So anyway, let me continue. Let him continue on. Here he goes.
But electrons don't move that way. Instead, they're found inside clouds surrounding the atomic nucleus. They move in all...
Again, that is partially correct, but the atomic nucleus is made of dipole electrons.
All directions, and the net effect is that the motion of the electrons doesn't generate significant magnetic field. What about the protons and electrons themselves? Back in 1922, in what is now called the Stern-Gerlach experiment, researchers proved that each electron is a tiny magnet all by itself. A decade later...
Exactly. That's exactly correct. Each electron is a tiny magnet. I think he's trying to jump into realizing that my stuff was correct. Listen to what he says.
Led by Otto Stern, showed that protons are magnets too. So maybe that's what makes a magnet? It turns out that the strength of a proton magnet is about 700 times less than an electron magnet, so we can ignore the protons entirely, at least from a magnet point of view. That leaves the electron. Are electrons what cause a magnet to be a magnet? Well, yes, but it's more complicated than that. To begin with, what causes an electron to be a magnet? The short answer is, well, nobody knows.
Well, I can show you what it is. I can't tell you why, but it's a black and white particle, and they are always attached together. They never will separate, and unless you force them to separate using generators or, like we did, accelerate them to where only the white can get through the accelerator. All right, so here he goes.
It's like other questions. Why does an electron have a wave and a particle nature?
I can tell you exactly why. Because it's a spinning particle. And here it is right here. There it is. It spins like this. All right, it's a magnetic particle and it spins. Now, it has the black and the white on it. Remember I showed you what a photon looks like? These are photons. And when they come through the accelerator, they split. The white part forces all the other white parts away, and that's what creates these what they call interference patterns. But it's a spinning particle. But if you looked at it from the side, it looks like a wave. Just like if you look at it coming through the air, you see a wave. Here's what you see. There's the wave. But inside there is the particle. But it's spinning, just tiny little spins. They're not huge, big like that. They're just tiny. Well, let me show you what they actually do look like. See what they look like. It's tiny. Now, this one's lit up because it's being forced into a bunch of other ones that don't want to be there. They hate each other, and they force each other to repel, and that creates glow. Glow is energy. Energy is heat. Energy is light. Energy is electricity. And we created all of those things right here by taking that pulse red laser, just going by, boop, 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 boop. Now it's starting to accelerate. But here it is the particle is in here, which I've shown you the particle, and there's the wave. Now, here's where it accelerates. This is where Einstein was wrong. They're all wrong. You can accelerate light. Very simple to do this. You put it through a venturi, and because it's accelerating, it's pulling the actual particle, which you couldn't see before. But now the particle is actually being exposed for what it is, and it's sucking itself right out of the magnetic field. That's exactly what happens in a jet fighter.
Roger.
Okay, a little interruption there, but let's get back to it. I think I showed you the light coming through here is banging into every other light particle, every particle there is, every gas, everything has fields around it when you bang into it. Look up the Casimir effect. It's field to field. Now, this is accelerating because of the venturi, and the venturi just does that. And I got to be honest with you, it sort of perplexes me how it does accelerate it, but it accelerates it like crazy, and it does. And that is where, and you can see the luminosity here is off the charts. Luminosity is energy. Just look it up. Luminosity is energy. The more energy, the more luminosity. It came from here with no energy and no luminosity to here with high energy and high luminosity, which means that if we could intervene and take that high energy right here, because it's completely separated. That's all you want is the white. We take that, pump it down in the batteries, we are good to go. Now, what happens coming out of here? This is where you get the Higgs fields, and here they are right here. So here we're looking into the accelerator. All right, they were looking like into this, and all in this white area there's just nothing. You can't see anything other than just these little spritzes of white. There's nothing that you can see, and then all of a sudden the fields show up when they concuss out here. That's where the black interacts with the white. That's all I can take away from this. Now, these are the particles, and these are in the acceleration phase to where they're photons. And then this shows you that the black, they can slow down. You see, and this shows a wave particle nature as well. There's a particle spinning and creating a wave. I think that's been pretty clearly shown. Now, if they want to look at something special, this is special. That's the only time I've ever seen this. And this white one here, I think, is a reverse spinning particle. And it is spinning in this direction, like this. And all the rest of them are going in this direction. And when it hit that, this spinning field, which is the particle sits out here, I believe the particles sit at the very outside, and they create these fields inward. Anyway, I believe this particle interacted with the outside field particle and has just spun it off, because this is going this way and this is going this way, and this, they hit together and it just tumbled this one off. That's the way I'm taking away from that after 7 or 8 years of looking at it, trying to figure it out. That one there, that one put me right off the edge. That was to have a little. There's a lot of things that take a long time. It's like this here. I looked at this for a year or more before I really had a pretty good grasp of what was going on, and I still don't, to be honest with you. This is, I don't know what to think, and this here just blew me away. This looks like a pyramid, and these look like the terrestrial boats going back and forth to Atlantis or something. I'm telling you, you never can tell anymore. I'm telling you right now. There's things we have no clue about. And what is this here? This is energy. It's got to be on top of the moon, or it's between us and the moon. And what is that stripe going down the middle of the, whatever it is? You know, again, and I've got a bunch of other ones to show magnetic fields in space. There's no way that particles are going to come through here without interacting and slowing down. It's just impossible. What we're looking at is not like never slowing down. Einstein broke physics. Everybody has to bow down to Einstein. Well, no, not anymore. It's quite obvious it's not true. All right, let's go to a little more of what Don has to say here. Particle or wave?
Why does it have an electric charge? Why does it have a mass it does? Why does it act like a tiny magnet? Why do people put ketchup on hot dogs? All of those are questions with no good answers. They're just facts for which we have...
No, there is good answers, Don. I'm not going to continue on with this whole thing because I've already given the answers, and I got to be honest with you, I would like to engage with anybody. Don Lincoln would be fine. Don and I didn't hit it off, and you know, we did engage for a while there, but everything I presented was dismissed as just being tinfoil hat stuff, and basically that's what he literally said to me. You're a tinfoil hat guy, and I'm not going to pay any attention to what you're saying. And I said, Don, I found your particles. I showed him all the things that I'm showing you, and this goes way back to then, way back. So all these particles back. This goes back to 2014, 2015, right around in that area. And again, this is what he found. This is what he said. This is 2013. I got a hold of him. I said, Don, we found your particles. Well, that didn't work out. And I said, you're right. The universe is filled with particles, the quantum foam. He calls it the quantum foam. And he says, and he's exactly right again. Subatomic particles winking out of in and out of existence just for like that. That's because they're just laying around out there, and some other particle comes through, an energetic one hits it, and it blinks it, and it goes away. That's why it's a quantum foam. It's just like a head, the bubbles on appearing and disappearing in a dizzying display of change. And that's why you look out in the Milky Way and all that, and you see like a glow. The glow is that dizzying display of change as these little particles get hit. And when they do, they slow down. That's why we're not getting the same speed of light here, and everything's expanding away. That's just nonsense. Everything is coming at us and just coming slower as it comes down. It's not like they're pulling the wave away, which makes it look slow. It's just getting slow. And again, Einstein, you got to get off that case. All right, I think I've shown enough to make the case that these two particles right here are magnetism. That's what magnetism is. And then you can shift all the particles down to one end of something that will allow that to move the electrons down and to gather at one end versus the other. And those are, as Don Lincoln said, the ones that are in the middle basically of the periodic table so that they can move one side or the other. So there's a lot I agree with him about, but there's other things I don't. And the thing I don't agree is, well, there's a lot of things. Just let's leave it at that. But if we could get free energy by doing this with laser through this and collecting it, you could run that all day long, 24 hours a day, never have to stop. And it's non-polluting. It's not it doesn't damage anything, literally nothing. So it's time, I think, to pay attention to this and at least look at it, because as again, these are the particles that that Don Lincoln was referring to. There's no question these are them, and these are the tiniest particles that exist as far as I can be determined. Although there was that one very, very crazy one, this one here, this thing here, I don't know what that is, but it's not a Higgs field, and it's not a dipole electron as far as I can tell, or maybe it is. I don't know. That's the craziest one. I've never seen anything like it before or since. All right, now what I am going to show you is something that is from a nuclear bomb blast. Now, remember this one here, where this is 100% white, nothing but white, and then all the black is waiting out here to reattach, and it starts attaching right out at this distance from the Venturi. Now, if the Venturi is not tuned exactly that way, a little black can get through, and this is what happened here. This is a different tune, and a little bit of black got through with it. You don't really see it until you see it right here. And what is it doing? It's pushing a wave out in front. Now, that wave does two things. First of all, you get the Whistler wave in front of it. That's what they call that, the Whistler wave. And it makes a sound. It goes, and you can hear it sound. And then behind it comes the white particles, which have no mass. They're not going to push anything down. They're not going to knock anything out of the way, but they're going to burn stuff. They burn. They incorporate into the non-massive white particles that are in there, and there's just too many white particles and they combust. There's too much energy between their fields. And then the black will come afterwards and knock the house down. So don't forget, it's going to go off. We're going to see, then we're going to see the house burn up and not move. And then we'll see the house go flying. But before, if you were listening, and I do have a video you can hear the Whistler wave ahead, and you hear, and then, I don't know, 30 seconds later, because they're far away, boom, the wave hits. So now we're going to look at this right now from an atomic bomb blast. So here it is right here. It's atomcentral.com. All right, and here's the house, and they have a camera facing this way in an enclosure, a hardened enclosure, so it's not going to get damaged, and it can watch what happens as the explosion occurs. So here it goes. I got the sound turned off, and it's running in very slow motion. The first thing you're going to see is everything's just going to go brilliant, and then you'll see these poles and wires and everything just fester up and fume up. Look at this. Nothing's moving. Nothing. The bomb has already gone off, and it's just nothing but I stopped it, and there's nothing but stuff vaporizing. All right, that means there's no mass. There's no mass to push everything away. The mass is coming next, which is the black particles. So it just burns and burns and burns and burns and burns. You know, and it's only take a second in real life, and then there goes the house. So that shows that those two particles can come apart, and I showed you that we actually had them come apart right here. There's no difference whatsoever to that thing. Here's where everything was brilliant, and then the next thing you know, everything burnt up, and then it got knocked down. Same exact thing. Okay, I'm going to leave it at this. These two particles, these are the dipoles, and two of them together make a dipole electron. Now, they don't see them the way we see them because we're working with these little tiny light particles, and they're working with just monstrous, huge particles. So I'm going to leave it at this. Don Lincoln's showing this, and if he wants to know really what magnetism is, I would like to discuss it with him, because these two are like the tiniest bar magnet that exists, and at this you can break them apart. Above this, you can't break a bar magnet apart. You can break it 10,000 times and you have 10,000 bar magnets. This, you're at the bottom of the capability to split. So when you split these two apart, they stay split apart. I mean, they want to come back together, but you can split them. Otherwise, you can never get just the electron part or just a muon part. It just doesn't happen. They're always glued together as Diracs, which I showed you. These are the Dirac neutrinos right there. All right, so, and that's, again, these are the smallest particles that exist. So, and they're made from light, so I really don't have much more to say about it, other than that I'd love to see some more investigation done into this possible device that could give us some, portable free energy, non-polluting, just free. If it works, I'm just guessing. At this point, that's a guess. All right, I don't guess a lot. When I make a statement, I like to make a statement that I can stand behind. But without doing the research, how can you stand behind something like that? All I can say is it looks pretty damn good to me. If you can create an increase in luminosity, you have increased the energy. That's exactly what you look it up. Luminosity is energy, and if we didn't increase the luminosity, I don't know what you're looking at, because it started back here with almost nothing, and back here you got explosion. This is pushing back against these. These are other fields that are coming forward, but they're not accelerated like this one is, because it's right dead nuts coming right down the center. These are coming, but they're just sort of drifting along like light normally does. It doesn't glow like that in the middle of the air. The only reason they're glowing in the middle of the air is it's pushing back at them. This is all very top-end stuff here. It's time to look at this with a new critical eye.